Hi everyone. So welcome to Turbo Machines, and we are studying this module number 3, that is impulse and reaction steam turbines. So in this we are going to study velocity compounding and advantages and limitations. So far we have seen the steam turbines and so definition part, and then so what is all about this steam turbines, what and all, how the velocity triangles are drawn, how the what you call the combined velocity triangles are drawn. So all those things we have seen. Now coming to this, we are going to see the different term called compounding. So which is velocity compounding. So here the compounding in the sense. So we will what you call check in the coming slides, compounding of turbines. So what we can say in the compounding of turbine is that if you take pressure, so certain pressure of the, if it is a huge amount of pressure is taken in a turbine, so it cannot withstand. So there will be a possibility of a breakage of blades. If you allow the steam, more high pressure steam is allowed to flow, so there may be a breakage of blades. So to avoid that breakage of blades, so we will do compounding. Compounding in the sense, we will introduce number of stages, not in one particular stages. Instead, so we will allow them to flow in number of stages. If we do this, so there will be the high pressure will be reduced, and then there will be less possibility of breakage of turbines. So that we will see in this what you call slide. So the high velocity of steam is allowed to flow through one row of moving blades. It produces the rotor speed of 30,000 rpm, which is too high for practical use. Okay, if you take one set of what you call moving blades and stationary blades, rotor and stator, so it has to produce a rotor speed will be 30,000 rpm, but so if it practically it is impossible for a turbine to rotate 30,000 revolutions per minute. Okay, so this is not possible. Hence it is therefore essential to incorporate some improvements for practical use and also to achieve high performance. So since it is not possible to make the turbine rotate for 30,000 rpm, so we have to come to think in a practical way how to achieve this the high performance. So for that, so this is possible so by making more than one set of nozzles. So if it is a one nozzle, so it will be very difficult. So if you introduce more number of nozzles and rotors in a series keyed to the shaft, so that either the steam pressure or the jet velocity is absorbed by the turbine in stages. So this is called compounding of turbines. What they are trying to say is, suppose if you take a turbine and if you introduce one nozzle and then one stator blades, one movable blades, that is moving blades, and then again another what you call nozzle and then another moving blades. If you introduce more than one set of nozzles and rotors, so then this kind of arrangement is called the compounding of turbines. So why this compounding is required is because to reduce the pressure, the steam pressure or jet velocity will be absorbed by the turbine blades at different stages. So that is nothing but the compounding of turbines. Now, so how that compounding can be done and what are the different ways this compounding can be done for the steam turbines? So the high rotational speed of the turbine can be reduced by the following methods. So what it is saying, rotational speed of the turbine, high rotational speed can be reduced by introducing these following methods of compounding. So what are those methods? One is velocity compounding, next one is pressure compounding, now the last one is pressure velocity compounding. So if you what you call when you do the compounding, so if you what you call take the velocity parameter into consideration, then it is called as a velocity compounding. If you think about this pressure, then it is a pressure compounding. If you combine both velocity and pressure, then it is a pressure velocity compounding. So we will see one by one so how compounding will be done. So this is the diagram of velocity compounding, and the example for this velocity compounding is a Curtis turbine. So in this figure, what we can see is the first we see a nozzle, and after that there is a moving blade, and then there is a fixed blade, and then again there is a moving blade. So that means one nozzle and one fixed blade and one set of moving blades are introduced here. So we are doing this velocity compounding. So what happens here is when nozzle, through nozzle steam comes out and first enters into the moving blade, and moving blade rotates because so it will be connected to the rotor, so moving blades rotate, and then since it is connected to fixed blades, again the fixed blade is also will act as a nozzle. So here another nozzle is introduced here. So in this fixed blade, again this steam enters and flows because it won't rotate. It will guide the steam how to flow and where to flow into this moving blade. So then the steam will come to the moving blade. So again it will rotate the rotor and then the remaining steam will go out. So during this process, so what and all that happens and what is the condition of the velocity and what is the state of this pressure, that we will see in the graph. If you look at the below diagram, the graph, so the first one what we can see is a pressure of steam entering at nozzle. And then the last one, the below what you call a horizontal line will show the velocity of steam entering. So pressure of steam entering and velocity of steam entering. So when steam enters into the nozzle, it will have high pressure. So it will have peak pressure. So that pressure steam goes inside the nozzle and comes out of the nozzle. So there will be, so since that exit of the nozzle, that area will be more than the inlet of the nozzle. Since there is a difference in area, since there is a convergent portion of this nozzle, so steam comes out and with what you call velocity, certain velocity, and then there will be a pressure drop takes place. So that is why the nozzle, there is an inclined line which is falling down. So that indicates the pressure drop. And whereas in the case of velocity, so with what velocity it is entering, the same velocity it will come out from the nozzle. And then, so what happens here is, so in the while coming out of the nozzle, the velocity increases. So the dotted line shows that the velocity increases and pressure decreases. So the same steam will enter into the moving blade. So when it hits the moving blades, what happens here is when the steam, their expansion takes place. When expansion takes place, what happens here is pressure reduces. So that's why, so pressure will remain constant over there. So what happens here is the pressure remains constant in moving blade because there will be expansion process. During this expansion process, the pressure remains constant. And what happens to the velocity? So there will be a velocity drop. Okay, so velocity comes down in the moving blade because while hitting the turbine blades, when it is moving, so velocity will come down. And then it will enter into the fixed blade. So when it enters into the fixed blade, so the same pressure will enter into the fixed blade. But what happens to the velocity? Velocity will remain same. When it is hitting the fixed blade, so the velocity doesn't change. So it will remain the same. That is why there is a horizontal dotted line will be shown in the fixed blade. After coming out of the fixed blade, it will enter into the moving blade again. So in this moving blade, again this velocity drop takes place since the blade is moving. And whereas in the case of pressure, pressure remains constant. When it comes out of the moving blade, if you check that, so the pressure of steam leaving will be very less. And whereas in the case of velocity, so it will be little higher than the entry of the nozzle. So velocity of steam leaving, so that arrow mark is shown over here. So this is the pressure velocity graph of velocity compounding. So what happens here is during this process the entire pressure remains constant. From nozzle, pressure drop takes place. From there, when it enters to the moving blade, fixed blade, moving blade, in these three blades the pressure remains constant throughout. But whereas in the case of velocity, so there will be a drop in the moving blade and then constant in the fixed blade, and again there will be a drop in the moving blade. So what we are doing is we are compounding. This is what velocity compounding. So in different stages, we are introducing different stages for this velocity compounding. So we will see the same thing here. This is a Curtis turbine. Why it is called as a Curtis turbine? Because it was first proposed by a scientist called C.G. Curtis. So that is why it is named after this particular scientist's name. So it consists of set of nozzles, so a few rows of moving blades which are fixed to the shaft, and then rows of fixed blades which are attached to the casing, right? Moving blades are, so you have to remember this. So a set of nozzles will be there, and then moving blades are fixed to the shaft. Always it will be fixed to the shaft, it will be moving, it will be rotating. And fixed blades which are attached to the casing. So it won't rotate, it won't move, it will act as a guide blade, and it is called as a stator. Okay, so in this velocity, this is the arrangement or the construction of this velocity compounding. And this velocity compounding, so first what happens, the high velocity steam enters. The first row of moving blades, what happens, velocity reduces, and then it will enter into the fixed blades. There will be no change in velocity. And then second row of moving blades, what happens, velocity reduces. Whereas in the case of pressure, there will be a pressure drop only in the nozzle. But afterwards what happens, there is no further drop of pressure as it passes over the moving blades. So next one is, so velocity compounding advantages we will see here. See, the arrangement has less number of stages and hence less initial cost. Arrangement requires very little space, and it is reliable, very easy to operate, and there is a fall of pressure in nozzle considerable, so the turbine itself need not work in high pressure surroundings, and the turbine housing need not be very strong. So coming to the disadvantages, you will see friction. If you take the different number of nozzles, there will be friction between the surface of the nozzle and the steam, so there will be more friction. Because of the friction, there will be less efficiency, because ratio of blade velocity to steam velocity is not optimum. And power developed in the later rows is only fraction of first row. First row will have more amount of power will be developed, and then the later part, so it will be not like the first row, so the power will not be developed. Still, all the stages require same space, material and cost. For all the three different stages, it will have the same space and the same material cost. See, even though the power is not developed when it compared to the first row. So these are the disadvantages of Curtis turbine. So we have seen in this video, so what is compounding and what is velocity compounding, how it is constructed, and what are the advantages and what are the disadvantages. In my next video, I will explain how the pressure compounding will be done. So thank you so much for watching this video.